All right, in our final video for Chapter 5, we're going to look at ideal versus real machines. Okay, and so kind of to summarize the formulas that we've developed in this chapter, we have things for real engines and Carnot or reversible engines. And we'll use Carnot and reversible interchangeably. And same for refrigerators, or if we choose to operate it as a heat pump. So, if it is reversible or a Carnot, it's going to be the thermal efficiency is 1 minus TL over TH. For something real, it's 1 minus the amount of heat transfer at the low temperature over the amount of heat transfer at the high temperature. And I'm putting these in absolute values because it just is easier to work with that way. So 1 minus. I'm always going to get something that's going to be less than the Carnot efficiency. Now I can do these same sorts of formulas for refrigerators and for heat pumps. And one of the key things is that these temperatures were all developed based on being an absolute temperature scale. So that's an absolute requirement, must be absolute temperature. So let's try applying this. So let's look first at a simple one. I have a heat source at 1100 Kelvin. That's an absolute temperature, so I'm set. A heat sink at 300 Kelvin. And I want to figure out what the maximum possible thermal efficiency for a heat engine is operating between these two reservoirs. So this is like I'm burning fuel at 1100 Kelvin and I'm going to cool things off by letting heat be released from my engine to the atmosphere at 300 Kelvin. So if I want the maximum possible, that means I'm looking for what is the Carnot efficiency, which is the one involving temperatures. So the reversible is 1 minus TL over TH. TL is 300, TH is 1100. Be sure you do the division and then subtract from 1. See that mistake a lot. And I get 0.727, or a lot of times we'll talk about it as a percent efficiency. So converting that over, 72.7% efficient. Now remember, I'm going to always get a number trapped between 0 and 1 for thermal efficiency. So let's look at another example. This is a heat pump. Now heat pumps are refrigerators where I'm taking the heat released by the system as the desired effect. So in this particular case, I have one operating between an outdoor temperature of 20 degrees Fahrenheit and an indoor temperature of 75 degrees Fahrenheit. So I need to be careful here because these are not absolute temperatures, correct? And I want to know what's the best possible coefficient of performance. So I'm going to use the one with temperatures, but I need to be sure I convert my temperatures over to degrees Rankine, or I could have gone to Kelvin either way. So adding 460 to the temperatures, I get my high temperature over my high temperature minus my low temperature. I get a coefficient of performance of 9.73. Now, one thing to notice is thermal efficiencies must be limited to 0 to 1. That is not the case for a coefficient of performance. These numbers are going to be more than 1. Okay? They can be very large, actually. Okay? So I'm going to be looking for large numbers in these cases. So let's do another one. This one, I'm not asking about maximum possible. This is a different type of problem. So I want to know the heat input and output for a coal-fired power plant, the type that we would have, say, here in Oklahoma. There's one just down the road, that generates 2,000 megawatts of power by burning coal at the rate of 8.1 times 10 to the 5th kilograms per hour. Now, in order to do this, I need to know the heating value of coal. In other words, when it is burned, how much heat does it provide? And in this case, it's 33,500 kilojoules per kilogram. Now, different coals will have different values, but for the sake of this problem, that's the value we will use. And we want to know the thermal efficiency. Now, this is not a maximum. This is not ideal reversible. This is the actual value. So I want net work over heat transfer in. Now this burning coal is going to be my heat transfer in. So I have a mass flow rate for my coal, and I have specific rate of heat transfer, that's really what this heating value is. And so the mass flow rate times Q sub H, or little q, is going to be my capital Q, okay? And the net work is my goal to figure out, okay, 2,000 megawatts. So this is my net work. I'm going to have these. I'm going to have to fix the units a little bit because I want this to be dimensionless. But net work over heat transfer N, the rate of m dot times little q, is going to be my thermal efficiency. So if we look at that, okay, my net heat transfer N, m dot times specific heat transfer, fixing the units here because it's per hour, so turn it into seconds. A kilojoule per second is a kilowatt. So I have 7.5 million kilowatts. Okay, now I chose to do the entire problem in kilowatts, which means that, okay, if it's going to generate 2,000 megawatts, I need to convert that over to 2 million kilowatts. Okay, just trying to keep things on an even playing field here, all the same sort of units. And so Q sub L is going to be, well, the net work, okay, minus the heat transfer N, because net heat transfer equals net work. Keeping in mind signs, I do end up getting something negative, okay? And so 5.54 times 10 to the 6 kilowatts will be lost by this power plant. The thermal efficiency is net work over heat transfer N. So 2 times 10 to the 6th over 7.5 times 10 to the 6th kilowatts per kilowatt. The units have to cancel, and I get 26.5% efficient. Now this is the efficiency that would really be experienced. This was how much power they produce, how much coal they burned. This is the actual efficiency. This isn't the maximum possible. In order to do that calculation, I would need to know the temperatures. So this concludes our study of Chapter 5. We'll be going on to some other definitions of the second law and looking at how they can be applied to processes, not just to cycles, in our next chapter.